Hello guys, thank you so much for being with me in another artificial neural networks tutorial video. Uh, okay, the more the number of parameters, the more complex the function. A more complex function may work very well on the training set data, but not well on new data. Here we have to use methods to fight over fit. We have seen one method in previous videos. We said that we will add a regularization sentence to the loss function to achieve this goal. By adding this sentence, we avoid increasing the parameters. For the case where the number of parameters in deep learning is very large, this statement is not enough. Another method that is used in deep learning for this purpose is the random deletion, random removal, or dropout. Consider this network. We multiply the inputs in each layer by the weights and then apply a nonlinear function on them. The idea of the dropout method is that during train, in the forward stage, after calculating the output of the hidden layers, we randomly select p% of the outputs and consider them as 0. We repeat this work in all hidden layers. This work is done only during train, and this is not done during the test because this is to prevent overfit, and overfit does not occur in the test phase. Since our layers are fully connected, when we set the output of a neuron to 0, the weights are multiplied by 0. It means that by removing each neuron, we have also removed all the connections of that neuron. As you can see in the implementation, we first do a multiplication and add with bias. Then we apply a nonlinear function on them, and in this way we will have the output of each layer. In dropout, we have to generate a random number for the number of outputs in each layer. We want to produce a mask. It means that some of them are equal to 0 and the rest are multiplied by 1. We want the probability of producing 0 to be equal to p. So the probability of producing 1 must be 1 minus p. So we compare the generated random number with 1 minus p. If this random number was smaller, it could be 1. On this p code, on this code, you can see. On this code, p is the possibility of keeping. It is considered to be the possibility of keeping. In some other packages, the possibility of removing. It is considered that the p is the possibility of removing. Different packages have different definitions, but the regions are the logics are similar. I have explained both so that you are familiar with both. Do not use dropout in the output layer. Pay attention to this point. Do not use dropout in the output layer. Now that, what is the benefit of this method? In the linear classifier, we directly predicted the classes from the images, from the inputs actually. But in neural networks, we generate higher level features and predict classes from those high level features. These hidden layers in deep learning take the lower level features and perform calculations on them and produce higher level features. These features that we calculate in the last hidden layer are very high level features. That is, for example, in the last hidden layer, there is a neuron that determines whether the image has ears or not, for example. Now, when we randomly set the outputs to 0, we are telling the network that you don't have to have all the features to be able to recognize the right classes. In fact, somehow we eliminate the dependence on a feature that we have for a classification and increase the ability to generalize. Another interpretation is that instead of one neural network, you are training more neural networks. In this example, we have 3 layers containing 5 neurons. Each of these neurons has a probability of 0.5, a half. It means that each neuron has 2 states. That means we have 215 states. We call this concept ensemble learning in machine learning. That is, we consider the opinion of each model and take an average between them. For example, when someone is diagnosed with a disease by a doctor, the patient is not satisfied with the same doctor. He or she asks the opinion of several doctors. We said that we do this only during the train. So when we give the same data to the algorithm during train and give the same data to the algorithm to the model during a test, we will have 2 different results, because during train some neurons have been deleted. We have to solve this problem. Suppose p is equal to 0.5. In each layer, on average, we zero the output of half of the neurons. We consider 0 for the output of half of the neurons. If we multiply the capped neurons by 2, the input of the next layer is the same as what happens without a deletion, without this removal. Because in this way, the weighted sum of the input will not change. Almost will not change. In general, we have to divide the remaining neurons by 1 minus p. Again, in the implementation codes, we have considered the case where p represents the fraction of neurons that are kept. But finally, we have to divide the neurons exactly by p itself. If you consider p as the percentage of neurons that are kept, you should have a division by p. And if you consider p as the neurons which are the number, the fraction of neurons which will be deleted, so you should divide by the 1 minus p. This interpretation has a mathematical justification that you can see in the slides, but in all the implementation codes in the slides, p is the probability of retention and not deletion, probability of keeping, not a deletion. But there is no difference. You should know the logic actually. Okay, we will have just one other video in this tutorial. I highly recommend you not to miss it. Have a nice time.